Let's now cover lecture 10. We're going to look at transformation really quickly. It will be a short video. Just and it's a summary of what we covered already on how to transform second order tensors. But let's look at stress and strain transformations. And why it's important to transform them is because you may need to transform the stress and strain for predicting failure. It's useful to transform the strain to measurements are useful quantities. You may have strain gauges and you need the strains in a different direction. And it is also used in the analysis of composite materials, for which I had a number of video lectures in YouTube that you can check it out. So we let's say I have a plate and the composite material has fibers oriented this way, and there's a single laminate. You can calculate the direction cosines as the angle between the 1 prime and 1, the 2 prime and 1, and so forth. And so yeah, so that's how you calculate the direction cosines, is finding the angles between the new coordinate system where you're interested in finding the information to the original coordinate system. So you can always perform these transformations by using these direction cosines. And I'm moving quickly because we kind of covered that before, but I'm showing you in graphical format. And so the cosine, now say I want to find the cosine between the 1 prime and 1, that angle can be found as alpha. So that's why I have a cosine alpha there. If I call this alpha as an example, because this is a one direction, so that angle is alpha. And then if I want to look at the angle between 2 prime, which is this one here, and the 1 direction, so that'll be this angle here. That's a complementary of the angle, so clearly that's minus sine of alpha. And then the angle between, and you can see here, the angle between 3 prime and 1, the angle is 90 degrees. So cosine of 90 is 0. And I can keep going on and on and on until I get here, for example. That cosine between the 3 prime and the 3, that angle is 0 degrees. So the cosine of 0 is 1. And so that's why you don't see a change there. You just get 1. So that's my direction cosines now. So I'm ready to now transform from the prime system, from this system to the prime system, to the new system, where I can calculate stresses there. You can simply perform these transformation that we already discussed. If I call Q to be the same thing as A, and I apologize for changing the convention on you, you can use A, which is Q in my new convention that you showed you, to calculate this transformation. You can multiply everything out. So if I call the direction cosines L1, M1, N1, and I'm doing it just to have numbers or variables there, this is fully known. So you know, these are all numbers. So I can then calculate and expand this, and this is what you will get for the new transformed stresses. So if I know the stresses in a coordinate system, I can use the direction cosines Q, and I showed you how to calculate direction cosines, which is right here, and I can calculate then the stresses in a new coordinate system. So that's a way to do it. I have expanded it here, and I actually wrote it in terms of X, Y, and Z, so it's easier to see, but you can just use index notation just fine. And so you may have seen these formulas in mechanics of materials. So if you have just a simple transformation in 2D, so that angle transformation is just theta. So then you can use this formula here on this page, substitute what Q is, and you will find exactly what I have here in any mechanics of materials book. But the question I showed you is a lot more general, because it can be, you can rotate 3D in 3D. I can do the same thing for strain transformation. So if I know that strains in a particular coordinate system, I can transform it to a new coordinate system, and then you'll then get you'll be able to do it, and then you will match the mechanics of materials equations you've seen before. Other coordinate systems that exist, you're going to have curvilinear coordinate system. Here you have z's always pointing up, and then this is the radial direction. That's a circumferential direction, and this one always points upwards. So this is the strains that you will get in that particular coordinate system. When you look at the coordinate systems for, say, cylindrical, this is what you will get. Notice how there's a radial deflection, the circumferential deflection, and then the deflection in the z direction. So yeah, so the strains look different. I can go to cylindrical coordinate systems, and this is what I'll get for stresses. The equilibrium equations become this in a different coordinate system. These are easily derived by using the basis for the cylindrical coordinate system. Then I have the spherical coordinate system. In the spherical coordinate system, you have R as a radial component, but then you have two phi that define the location in the spherical coordinate system where you're looking at. So phi and theta correspond to the azimuth and the circumferential direction, while R is a radial direction. The equilibrium equations look a little more complex, but nothing to fear because these come from straight transforming a regular Cartesian rectangular coordinate system to a spherical coordinate system. And then you can also look at Hooke's law. Hooke's law is going to look the same, doesn't matter which coordinate system you're working on. So this is not going to change at all. It should be invariant to any, this is going to be the same. Spherical or cylindrical, the same coordinate system. The only thing that's changing is how you define the strains and the stresses. And material symmetry, I want to just point out a few more things. So there is something called the monoclinic material, which means that if this is the plane of symmetry, that the material behaves the same in the x3 or x3 prime. This one will bring the 21 independent constants to 13. So it simplifies it further. So here I show you how to use a stress tensor, transforming the stress tensor, using this idea of transforming x3 prime, because we know at x3 and x3 prime is the same. So monoclinic material behaves the same in the x3 or x3 prime. So I can use that relationship. And when you work it out all, you'll find that the stress the constitutive law is going to have a bunch of zeros here and here. And that will represent monoclinic material. So you have to calculate these 13 independent constants. Remember that these constitutive law, the C matrix is symmetric, but you can calculate those constants through testing. And then I have an orthotropic material, which is already covered, but you'll have 9 independent constants. And so, yeah, so with that said, you have a great rest of your day.